history of the machine frontier is it attracts people who are prone to bravado, great confidence, strong personalities, but we know now that that has to be held in check. Instead, that has to be tempered with respect, with humility, and with concern for the workers.
Step off the limb now. That's one small step for man, one giant leap for mankind.
Even as Neil Armstrong and the others who followed him were walking on the lunar surface, the NASA program that had taken them on their amazing journeys was undergoing wrenching changes. The budget for NASA's hugely successful Apollo program was being slashed. By the early 1970s, NASA desperately needed something new to regain support. In the game of money, power, and prestige that is played in Washington politics, NASA's seat at the table was now on the line.
The Apollo program, a mighty achievement, is now winding down. NASA looks inside itself and says, what do we do now? How do we follow and act like that? We had all those engineers, administrators, great prestige, great pride in what they had done. We needed something else to do in space. The Space Shuttle was the answer.
NASA engineers came up with a concept that they believed would assure the continuation of manned spaceflight for decades. It was known officially as the Space Transportation System. The public would soon know it as the Space Shuttle. The shuttle concept was sold as a reusable craft that would allow the nation to continue space exploration. And it would do it without spending the billions of dollars on rockets that had always been destroyed, falling to Earth after spacecraft reached orbit. And best of all, the shuttle would pay for itself.
Apollo was pure R&D, but the shuttle was put in the position from the beginning of needing to pay its own way. If they launched a certain number of missions a year and carried payloads, and the word payload is very significant here, they got money from the Department of Defense, from scientific institutes for carrying experiments.
The planners were so optimistic about the shuttle, they were confident a mission could be launched each week or two. Congress approved the budget, and the first of 4 shuttles went into production. The shuttle that was sold to Congress was to be a huge integrated system. The orbiter itself was a stubby-winged aircraft about the size of a commercial DC-9. It would be bolted to a mammoth fuel tank filled with liquid hydrogen and oxygen. The orbiter was to be wedged between 2 solid rocket boosters that would top off its power at 7 million pounds of thrust. Once lit, this incredible propulsion unit would burn 2.2 million pounds of fuel in just 2 minutes. After they were used up, the solid fuel boosters would be jettisoned for reuse. Only the giant liquid fuel tank would be disposable. The Space Shuttle is arguably the most complex machine ever built. 2.5 million parts must combine to hurtle a craft weighing 2,000 tons into orbit, hundreds of miles above the Earth. After the mission, the entire magnificent machine must survive a return to Earth that would require it to go from 18,000 miles per hour to 0 in the time it takes to wash a load of clothes. The first shuttle to take off was the Columbia in April of 1981. But as the headlines subsided and the public began to take the shuttle for granted, problems appeared. It was clear almost from the start that the shuttle could never keep the ambitious number of flights per year NASA had promised. By 1985, launch facilities NASA intended to be busy every week were sitting idle. Managers became frantic to speed up the lagging number of launches. 60 missions had originally been predicted for 1985. The number to actually lift off was only 9.
NASA hoped, promised, wrote papers to the effect that in time the shuttle would become as reliable and as frequent a flyer almost as an airliner. But it was clear to people on the inside that this was a whole different animal.
The shuttle program was in trouble. Its budgets continued to be cut by Congress while its costs were increasing.
The original sales pitch for the shuttle, as I remember it, promised payloads in orbit for around $100 a pound cost. The actual cost has always been around $10,000 a pound, and it still is. So that's another measure of how far off NASA estimates were.
All of the goals of the shuttle program were dependent on its success as a business. Without a high number of launches, that success was impossible. The pressure on NASA leaders to increase flights was enormous.
They were pushing the Space Shuttle system too hard, striving towards a launch rate of 1 every 2 weeks. Really, we know now, an impossible goal, stressing the system way beyond its limits.
Trying to achieve an enormously ambitious goal with too little money and in too little time was all something the world had seen before. Unfortunately, few people at NASA were old enough to remember the story of another aircraft that struggled to fly almost 60 years before. In 1924, the British government set out to create a machine that had much in common with the Space Shuttle. The machine would be a 700-foot-long dirigible that could carry passengers and tons of cargo to all parts of the British Empire. The spectacular new dirigible would be called the R-101. Like NASA's Space Shuttle, the R-101 was born out of great national aspirations. Like the shuttle, the R-101 was plagued from the first with being behind schedule. And like the shuttle, the great dirigible was rushed forward without acknowledging many signs of danger. The R-101 was the largest airship ever built to that time. Beneath the skin of the ship, a steel frame held 16 bags. Each one weighed half a ton and was filled with highly flammable hydrogen gas. 5 enormous diesel engines supplied the power. But in creating extra margins of strength and power, the designers had built in its great weakness. Initial tests revealed the R-101 was 23 tons too heavy.
This was a ship running on the ragged edge even under ideal circumstances. A calm summer day had so little spare lift that motoring around, the crew had to dump fuel to stay in the air.
Lord Christopher Birdwood Thompson, the Secretary of State for Air, was obsessed with demonstrating Britain's great dirigible to the world. In the summer of 1930, he brashly ordered the R-101 to attempt a maiden voyage to India.
Lord Thompson had decided this project had gone on long enough. It needed to get into the air, even though the people closest to the project said this airship is positively dangerous.
To show his confidence, Thompson was a passenger when the giant airship took off on the stormy night of October 4th, 1930. By 2 a.m., the dirigible had made it to Beauvais, France, but was rapidly losing altitude. It barely cleared the roof of the town's Gothic cathedral and soon crashed into nearby trees. The explosion swept through the R-101, killing 48 men, including Lord Thompson. All who died were victims of Thompson's impatience and unwillingness to place safety before schedule. "56 years later, it was also schedule that continued to torment the Space Shuttle program. And on January 27, 1986, what was to be NASA's next launch had been delayed by 3 days of weather and technical holds. The press began to criticize the delays.
NASA fails to get it up one more time. It's the typical reaction. People did not understand that, in fact, the reason they didn't go when they were supposed to was usually because there was a safety issue. They were concerned about launching, but delays got interpreted as failure.
The shuttle Challenger would be making this flight, and it was intended to be a public relations showpiece. In addition to plans for several experiments and delivery of a satellite and telescope into orbit, the shuttle carried a special passenger, a high school history teacher named Krista McAuliffe.
Well, I am so excited to be here.
McAuliffe was to be the third amateur astronaut to fly in the shuttle and would report the wonders of space to her students watching and listening below. This latest liftoff date was also timed to allow President Ronald Reagan to mention its successful launch that night in his State of the Union speech. NASA needed a perfect flight from Challenger, and it needed no more delays. But now, yet another problem had developed. Engineers were worried about the weather. As early as 1981, shuttle flights had shown that the safety of critical O-rings in the solid rocket boosters was jeopardized by cold weather. O-rings were round rubber gaskets resting in joints between the three sections of each solid fuel booster. Their purpose was to keep the hot gases of the rocket's combustion from escaping from between these sections. The thin rubber circles of the O-rings were all that stood between the booster's 5,000-degree heat and 500,000 gallons of incredibly explosive liquid fuel. Engineers had come to the conclusion that these O-rings would become brittle at a temperature of 53 degrees. Now, on the night of January 27th, Challenger sat poised for launch the following morning. Weather reports called for a liftoff temperature of 26 degrees.
A skeptic is one who knows the system and yet knows what doesn't fit in. And that's the kind of attitude, that's the kind of people that we want right in the middle of our complex, high-power systems. People who will raise informed, tough questions.
By the mid-1980s, NASA was having big trouble keeping the shuttle program on schedule. But when they did manage to get the orbiters into space, they had proven to be a success. Research was being conducted, satellites were being launched, astronauts were becoming more adept at working in space. In spite of their growing frustrations over the delays, NASA was also growing ever more confident in the marvelous machine they had built. Perhaps too confident. To build such a machine was a stunning accomplishment, but in its very technological prowess lay its greatest potential for disaster.
What we know about complex technical systems, like the shuttle system, is that the more complex they are, the more they are likely to have flaws. And we know the same thing about complex organizations. The bigger, the more difficult it is to retain a kind of a culture that's resistant to error.
January 27th, 1986. After 3 days of delays, the Challenger waits to become the 25th shuttle mission. But now, on the eve of one of the most important launches in its history, the NASA organization had to deal with engineers who were insisting that the Challenger should not go up. The weather forecast for Florida called for cold. 1,800 miles away in Utah, that forecast worried engineers at Morton Thiokol, the builders of the solid fuel boosters. They were worried that the cold could cause O-ring seals in the boosters to fail.
On the night before the Challenger launch, this issue came to a head. Thiokol asked for a meeting over a telephone line with NASA, and the solid rocket manager told NASA that he could not sign the papers for launch.
NASA management was concerned about setting a precedent of 53 degrees as a limit for launch. They wanted no more obstacles to getting this big bird up in the air.
It became very heated. Thiokol engineers were challenged on almost every engineering point. Engineers were arguing that they shouldn't go. Manager was saying, well, where's your data? And they didn't have real data. They had intuition and hunch, which didn't work. It was not listened to.
The burden of proof, then, is on those who would want to stop the flight, because it's a bad thing for you. It's a bad thing for your mission, for your reputation, for NASA to have to delay again. There was a lot of that going on.
Thiokol engineers were intimidated. One NASA manager shouted, "The next thing you know, I won't be able to launch until next April."
This meeting was very difficult. At one point, NASA asked a manager at Thiokol to take off his engineering hat and to put on his management hat, as if that would make the decision more clear, the risk more acceptable.
By the end of the meeting, pressure from NASA managers to keep the launch on schedule proved too much. After discussing it amongst themselves, Thiokol officials came to a decision.
They went back on the teleconference line and said, "We've reconsidered, and we've decided to recommend launch."
There was a degree of confidence in management that we knew what we were doing, and when they didn't hear the screaming and hollering from someone down below that we absolutely should not launch, management said to themselves, "Well, we believe that we have a safe system," and they proceeded on.
January 28, 1986. A cold dawn revealed a NASA launch pad covered with ice. With hindsight, it seems impossible to believe that a decision to launch in these conditions could have been made. But it had been decided. Bureaucratic goals would take precedence over caution and safety.
Followed by Christopher Masala, Teacher in Space.
The Challenger would lift off as planned. Engineers closest to the data had been talked out of their objections. They had been required to prove their worst fears were true, rather than NASA proving they were not. But NASA had conditioned themselves to rationalize dangerous problems for the organizational goals of the program.
Very dangerous. NASA got on a slippery slope. One step at a time, they went from expecting there to be no damage to having some and then accepting more and more. So on the eve of the Challenger launch, they made the decision to go, and it was just one more step in a procedure that had started quite a long time before that.
NASA was gambling that the shuttle had never failed and wouldn't fail this time. 7 lives now hung on that gamble.
10, 9, 8, 7, 6. We have main engine start. 4, 3, 2, 1, and liftoff.
You're watching Inviting Disaster on Modern Marvels.
The disasters that I write about and that continue to unfold attract enormous media attention for a few days, for a few weeks, and in a few cases, continued attention for a few months. But in all those cases, the news cycle moves on before the full set of lessons emerge.
T-minus 10, 9, 8, 7, 6. We have main engine start. 4, 3, 2, 1, and liftoff. Liftoff of the 25th Space Shuttle mission, and it has cleared the tower.
If all disasters are preceded by hints, what was about to happen to Challenger had been preceded by voices pleading to postpone the mission.
Control program confirmed. Challenger now heading downrange.
Demanding proof instead of listening to caution, NASA had gambled that the frigid O-rings in the solid booster would hold.
Engines beginning throttling down now at 94%.
58 seconds after liftoff, NASA lost the bet. A small flame emerged from the right solid rocket booster in one of the joints supposedly protected by its O-ring. Deflected by the force of air rushing past, the flame was turned against the side of the main fuel tank. Seconds later, Challenger disappeared. As families of the astronauts looked on with first confusion, then horror, the solid boosters flew off in wild contrails. NASA managers could only watch in stunned silence as the crew compartment tumbled through the smoky clouds.
Flight Throttle, go ahead. RSO reports vehicle exploded.
The compartment would take over 2 minutes to fall into the sea.
Copy.
Any astronaut going into space on board the Space Shuttle is sitting on hundreds of tons of explosive material. It is riding a controlled explosion into space. These people should not have died. There were many opportunities, clear warnings the night before not to launch.
We thought we'd solved all the problems and that we were really operating to the best capability of the system. What we didn't realize, it's the little things that come up and bite you. O-rings.
The nation lowered its head in shock and grief. They had been led to believe that flying the shuttle was routine. Even a high school teacher could go up. Now that teacher and her 6 companions were dead. The public wanted to know why. A presidential commission headed by former Secretary of State William Rogers set out to find what had happened. As the inquiry began, NASA was not always forthcoming about what went into the decision to launch Challenger. In the first days after the disaster, NASA officials downplayed the significance of the O-rings and suggested other causes. When questioned by the commission, NASA made no mention of Morton Thiokol's initial refusal to sign the order for the launch because of worries about the O-rings.
We're particularly interested in the weather conditions, how they may have affected the launch.
But little by little, the facts of Challenger came out. After months of analysis, the Rogers Commission confirmed that technically the disaster was caused by the failure of the solid rocket O-rings. But the commission concluded the loss of Challenger was more about a flawed decision-making process than about rubber gaskets.
There was a lot of media attention about what were the causes of the Challenger disaster. What they thought, however, was that there was misconduct. What happened was actually much more frightening than that. There was no intentional misconduct. They did it exactly by the book, and they believed that they were correct and that it would be safe to fly. The flaw was not bad or incompetent or even evil people. The flaw was in the system itself.
In an effort to achieve the same mission with less and less money, NASA had gone from accepting no damage to tolerating a larger and larger margin for error.
The doctrine was to fly the shuttle, to fly it as frequently as possible so as to make good on NASA's claim of what they were going to be able to do.
In a world of higher expectations and lower budgets, management decisions were motivated less and less by the opinions of engineers.
And they lost touch with their own engineers and engineering knowledge. That, in fact, is what led them to start taking average citizens along for a ride. They didn't think it was risky.
Out of the commission report, specific changes were made to the shuttle program. Lives would no longer be risked to launch satellites that could more efficiently be put up with expendable rockets. In addition, NASA would abandon the concept of taking amateurs aboard flights. Krista McAuliffe would be the first and last teacher to ride the shuttle. Over 2.5 years after the investigation of Challenger, the shuttle was ready to fly again. Changes had been made at NASA, but as years went by, it was clear that many of the problems remained.
After Challenger, we had a change in culture in that they thought if they threw more manpower at a particular problem, you could solve it. What started happening is we got into the same mode that we were in prior to Challenger, in that we got overconfident and not doing our homework about little things. Then it's the little things that always come up and get you.
As the late 80s and 90s went by, NASA sent 87 more shuttles into orbit. The men and women who rode in them again dazzled the world with their accomplishments. With the shuttle's help, the International Space Station grew into a usable laboratory. In 1993, the crew of Endeavour repaired the damaged Hubble telescope, and always, research aboard the orbiter continued. But with all its successes, one part of the shuttle remained an accident waiting to happen. Among the thousands of components of technology that allow the shuttle to succeed, none is more important than the heat shield. Made up of tiles and carbon-carbon fiber panels, the shield is all that stands between the crew and the deadly heat of re-entry. The good news is that the ceramic tiles and panels can absorb enormous heat. The bad news is that they are very fragile. Debris hit and damaged tiles and carbon panels over 2,000 times in the first 33 flights of the shuttle. In 1990, NASA asked a risk analysis team to analyze the life-protecting heat shield.
So what did we find? Well, we found at the time that about 10% of the overall probability of an accident could be attributed to the heat shield. So that was a relatively high contribution. We also found that a large proportion of the risk was attributable to a relatively small proportion of the tiles.
The report noted that tiles covering the wheel wells, and particularly the tiles and carbon-carbon panels along the leading edges of the wings, were the most potentially dangerous. If the tiles or carbon panels in these sensitive areas were lost or even severely cracked, heat could quickly penetrate the orbiter body and destroy critical control functions. The fragile nature of the heat shield meant that any blow by a foreign object during the mission could be disastrous. NASA had always been concerned about damage from asteroids or space debris while in orbit. But the tile research brought another threat which NASA would not acknowledge. The orbiter is attached to the main fuel tank, which holds 500,000 gallons of liquid hydrogen and oxygen. To keep this fuel at a temperature of over 400 degrees below zero, the huge tank is covered in 6 inches of foam insulation. On liftoff, the foam on the tank becomes frozen and hard as rock. The shuttle program is cautioned about the danger of this foam hitting the orbiter. NASA chooses to do nothing about the potential problem.
It's this overconfidence that you can see happening in, oh, well, if we miss it, the shuttle is very robust, it'll handle the situation. And that's also what the flight controllers were thinking about the tiles whenever the debris struck the tiles. The analysis they had done said that there's not a problem with this, so press on.
For almost 10 years after the report on the tiles, the Space Shuttle program did press on. In January 2003, NASA prepared to launch its next shuttle mission. The orbiter will be the same Columbia that had made the very first shuttle trip. The crew of this trip will again be a mix of dedicated and very talented pilots and scientists. Typically, it is a diverse group that includes an African American, an Israeli, an Indian, those who had flown on other shuttle missions, and 2 who had never been in space before. The Columbia will carry them into orbit, where they will conduct 14 days of experiments ranging from analyzing dust storms in the Middle East to studying prostate cancer cells. The astronauts will also conduct experiments suggested by high school students from around the world. On the morning of January 16, 2003, a NASA space shuttle sits poised to go into space for the 113th time. Like dozens of their colleagues before them, the Columbia astronauts board their spacecraft and prepare to take the most exciting ride in the world.
We have booster ignition and liftoff of Space Shuttle Columbia with a multitude of national and international space research experiments.
Once again, the world would thrill at watching this amazing machine slip the bonds of gravity and climb into space. And once again, it appeared to be a perfect launch.
Columbia now rolling on to the proper...
But no one had noticed that as the monstrous rocket roared off the pad, a piece of frozen insulation had broken loose from the fuel tank and smashed into the left wing. The piece of foam was no bigger than a suitcase.
Houston now controlling the flight of Columbia.
But its effects would take 7 lives and threaten the entire shuttle program.
I have a lot of respect for NASA and what they've done. I've attended the space shuttle launches and thrilled to it like any other person within hearing range. But I think NASA has to confront directly the criticism from well-motivated people that the space shuttle has become a hood ornament, a symbol, a luxury.
You can see the Earth kind of at the top of the screen there. We're looking to the left side of the orbiter when the radiator on the left payload bay door comes up.
The Columbia has reached orbit successfully, and the crew is well into their routine when engineers at NASA realize that something potentially dangerous has happened on liftoff. They have finally seen the video that reveals the suitcase-sized hunk of foam hitting the left wing of the orbiter. The question is, how bad is the damage? Launch video suggests any damage would have been under the wing, so the Columbia's crew cannot check the tiles themselves without an unplanned spacewalk. The shuttle has no power to be able to move into a new orbit so that astronauts riding in the space station could inspect the wing for damage. Engineers at the Johnson Space Center in Houston can only guess at the potential damage by analyzing the puff of dust made when the foam hit the shuttle. They urgently request that satellites be ordered to take photos of the wing. If terminal damage is confirmed, NASA leaders would face a choice of doing nothing or attempting a high-risk rescue mission. But the choice becomes unnecessary when the head of the mission management team, Linda Ham, decides to cancel the engineer's request for photos.
And it makes me wonder whether an attitude might have set in, well, why do we need to photograph? Because what will we find out? What will we do if we see fatal damage? What are we going to tell the astronauts?
It is now certain that at some time during liftoff, the leading edge of the left wing was damaged. Additional carbon fiber fell off in space. This leading edge is protected by a carbon-carbon fiber that, like the tiles themselves, resists heat. Without it, the inner structure of the orbiter is completely vulnerable. Knowing nothing about the possible threat to their spacecraft, the crew of the Columbia allow themselves the fun of being part of one of humankind's greatest adventures.
Here comes the Superman entry of the astronaut floating around. We have SPS-107 coming into the module. He's here to do some house cleaning duties.
But life on a space shuttle is mostly about research. High school students in Syracuse, New York wanted to know if ants move faster in space than on Earth. Columbia proves that they do. A combustion experiment studying possible sources for low-power engines manages to produce the weakest flame to ever continue burning. Dr. Laurel Clark looks at cell cultures for cancer research. And Mike Anderson analyzes respiration and heart rate in space. It has been a successful flight, but after 16 days, the time arrives to come down. Saturday, February 1st, 2003, 8:15 a.m. Eastern Time. Somewhere over the Indian Ocean, Commander Husband is given the order to commence re-entry.
We're taking out, we get the rocket power on, we're working through the rest of it as well, thanks.
Rockets fire to slow the shuttle speed of 20 times the speed of sound. Computers reorient the aircraft to a nose-up position. As it crosses over Hawaii, Columbia begins to re-enter Earth's atmosphere in a descent from which there is no turning back. Few machines are put through the stress demanded of an orbiter returning to Earth. The friction of the growing number of molecules in the atmosphere rapidly increases heat on Columbia. The orbiter is moving from 100 degrees below zero to over 3,000 degrees in minutes.
This is amazing. It's really getting really bright out there.
Columbia's crew can watch as gases outside the windows turn from pink to red to a searing white.
Yeah, you definitely don't want to be outside now.
All of this is routine. Shuttles have gone through it 113 times. But somewhere over San Francisco, the re-entry stops being routine.
FYI, I've just lost 4 separate temperature transducers on the left side of the vehicle.
Where is that instrumentation located?
All 4 of them are located in the aft part of the left wing.
Temperature sensors in the left wing's hydraulic systems have stopped working. Minutes later, the temperature in the wing's landing gear jumps up 60 degrees. And shortly after, all communication with the orbiter ends abruptly. Flight controllers desperately try to get some response from the shuttle.
Columbia, Houston, UHF comm check. Columbia, Houston, UHF comm check.
Looking up at the morning sky, observers in Texas already know why the Columbia is not responding. Once again, America grieves at the loss of 7 talented and dedicated people. And once again, authorities turn their attention to asking the sad question, why?
It's easy to get the full attention of political figures and of news commentators in that first bright light of publicity. The real test of our resolve as a society to do better is how much follow-up is there when the news cycle has moved on to other things. Is there really an earnest investigation? And even more so, what do we do with those lessons?
May 6, 1937, Lakehurst, New Jersey. Like the Space Shuttle 70 years later, the German dirigible Hindenburg has enjoyed great technological success. On this spring evening, the Hindenburg is completing an uneventful maiden voyage across the Atlantic. But also, like the Space Shuttle, Hindenburg's success is deceptive.
The back motors of the ship are just holding it just enough to keep it from approaching the flight. Get it started, get it started. It's fighting and it's crashing terrible.
It took only minutes for the Hindenburg to become a smoking mass of rubble.
I believe that this is terrible. This is one of the worst catastrophes in the world.
But in those minutes, decades of work and research came to a shuddering halt. Commercial flight in dirigibles, what had been an entire category of aviation, vanished with the Hindenburg.
Explosion and fire shut down the notion of using lighter-than-air aircraft as mass transportation. Never again would people ride such airships. Time will tell whether the loss of 2 of the shuttle fleet will spell the end to this phase of manned spaceflight.
March 2003. The loss of 7 more NASA astronauts comes as a surprise and shock for some people. But for others, another tragedy in the shuttle program has been only a matter of time.
Columbia definitely was not a surprise to me. I had been saying for a long time that this was going to happen.
The woods and fields of East Texas are combed to find clues to what had destroyed Columbia.
Welcome to our first Washington press briefing. I will turn you over to Admiral Hal Gaiman.
Good afternoon. Obviously, the board is toward the end of its transition.
The investigating board is headed by retired Admiral Harold Gaiman. His job is daunting. Tracking down the cause of Columbia's loss will be very difficult. It was clear that foam had hit the shuttle, but this was not conclusive proof that it caused the breakup. Experts differed on whether a small piece of foam could cause the destruction of Columbia. NASA officials in particular seem eager to discourage the theory that foam falling from the fuel tank could be the cause of such a massive failure.
Right now, it just does not make sense to us that a piece of debris would be the root cause for the loss of Columbia and its crew.
Well, we shouldn't be so quick to rush to that kind of judgment. I think what we were seeing is a very common reaction among organizations following a disaster, which is to circle the wagons.
The board decides that they will have to organize a test to get more evidence. They need to see if they can find the smoking gun to the Columbia disaster. 4 months after the accident, a piece of foam is fired from an air-powered cannon at the leading edge of a shuttle wing.
3, 2, 1, 0.
Even untrained eyes could see that the foam had cracked the carbon-carbon panels on the wing's edge. But some insisted that this level of damage could not be counted as proof. A second test was ordered.
3, 2, 1, 0.
This time, there is no mistaking the effects of the foam.
I believe that we have found the smoking gun. I believe that we've established that the foam block fell off of the external tank was, in fact, most probable cause of the Columbia accident.
It was now clear that the foam had damaged the leading edge of Columbia's wing. This allowed the scalding gases of re-entry to burn through the shuttle's skin and penetrate the interior of the wing itself. There, the heat melted the aluminum structure of the wing. Aerodynamic forces then pulled the orbiter apart. But as with Challenger, the deeper roots of the tragedy were not found in physical breakdowns. The report of the investigating board stated unequivocally that NASA's organizational culture and structure had as much to do with the accident as foam insulation.
Challenger.
The bad habits from the time of Challenger had returned. Overconfidence was one of those habits.
The Columbia project manager said that they had been having tile problems all along, but they were comfortable with that. Comfortable is not what you want to be.
The report noted that opinions dissenting from NASA's upper management were not tolerated. The result was that ideas and potentially useful criticism were being squelched. Even more damning, the report stated that unless serious changes are made, the stage is set for yet another NASA catastrophe. The investigation board supported a return to flight for the shuttle at the earliest date, but only if serious changes are made in NASA's safety standards and patterns of management. For some, the system and the machine are too deeply flawed. For the first time in its history, many people question whether the time has come to end the shuttle program and perhaps even abandon manned space exploration altogether. As the Space Shuttle has succeeded, it has symbolized like nothing before it our ability to conceive and create amazing machines. But the shuttle program has also displayed the unfortunate human tendency for impatience and bureaucratic inefficiency. The problems lie not with the machines, but with our own imperfect ability to manage them.
We cannot go back to the farm. There are too many people on Earth with too many expectations of the life that we have built for ourselves. And technology is how we feed these people, how we keep them safe, how we medicate them. So I am not one of those people that say technology is the enemy. Instead, I see technology as a tool that needs to be used in the right way.
Will we continue to see a shuttle program plagued with dangerous problems and prone to unnecessary accidents? Or will we at last learn from our mistakes and demand that an amazing machine head for the heavens without inviting disaster?